Hey audience, last time I debounced my switches to get glitch-free signals into whatever circuit I want to test. This time I'll be handling signals going in the other direction from the circuit I'm testing to the LEDs on the front panel. We normally think of digital circuits at a higher level of abstraction than other circuits. We don't even think of them as circuits really. We don't think about where current is flowing or what precise voltages are at any points. We just think of them in terms of some nebulous 0 and 1 values. We ignore current and only consider the logical function of each gate. And that's a good thing. It frees up brain space to think about what our design does rather than how it does it. It's one of the reasons why digital circuits are so attractive. But they are still electrical circuits, and sometimes that reality shows up and we have to deal with it. We normally think of the output of a gate as being an ideal voltage source, but there's always some non-zero source resistance to it as well. And inputs we think of as sensing the voltage, but there's always some non-infinite input resistance to them. When an output is outputting high, there will be some current flowing out of the output of one gate and into the input of the other. And when outputting low, there will be current flowing the other way from the input of the second gate into the output of the first. Because of this current, there's a voltage drop over the output resistance of the first gate, and this changes the voltage seen by the second gate. When we attach more inputs to an output, more and more current flows, and the voltage drops more and more until eventually it's below the minimum voltage that can be considered high, or above the maximum voltage that can be considered low. CMOS behaves differently, but for now let's consider TTL gates, since that's what I'll usually be using, and they behave less ideally. This can be a problem when we want to probe a digital circuit with an LED to see what's going on. LEDs can draw a lot of current, and if we draw too much current, it could potentially change the voltage we're trying to probe and stop a circuit from working the way that we'd expect. The solution is to buffer our LEDs behind something that draws much less current from the circuit. Typically this is done with an inverter, and the LED is oriented so that it's forward biased and lights up when the output of the inverter is low. This is usually done because TTL gates can sink more current into them than they can source out of them for reasons, and also non-inverting buffers aren't really all that common. When we do this, it'll still affect the circuit that we're trying to measure a little bit because the input of the buffer still draws some current, but it'll be much less than the LED would draw on its own, and so it usually won't break anything. So tell you what let's do. Let's build a circuit that has as many inputs as possible attached to a single output of a gate. And that will represent whatever circuit I'm trying to test or debug. And then we'll just put some LEDs on it and see what happens. So first we need to find out just how many inputs we can attach to a single gate output. Here we have the 7404 datasheet, and there are two tables here: operating conditions and electrical characteristics. Together they make up sort of a contract or a promise between us and the gate. The operating conditions are our end of the bargain, and the electrical characteristics are what the gate promises to do for us as long as we keep it within those conditions. The relevant bits in this case are the output currents and the input currents. So we can see when the output is high, it asks us to please not draw more than 0.4 milliamps from it. And when the output is low, it asks us to please not try to sink more than 16 milliamps into it. And we can also see that when you give an input a high voltage, it promises that it won't draw more than 40 microamps from that. And when you give the input a low voltage, it promises it won't try and sink more than 1.6 milliamps into it. So this means we can connect up to 10 gate inputs to one gate output before we run the risk of potentially putting the gate outside of its recommended operating conditions. Another thing to keep in mind is that these numbers are sort of like the sell-by date on your yogurt. They're a conservative estimate of the worst case you could expect to find in the real world, but that doesn't necessarily mean that these inputs will actually draw that much current, or even that the gates will stop working when we pull that much current from an output. So let's build a circuit that has the maximum number of inputs on a single output, and then start connecting even more to it to see just what happens.
So here's the test circuit I put together. It's going to be hard to see what's going on there, so I made a schematic. I also have a switch from my switch box that is connected to one of the inverters on one of these 7404 chips, and the output of that has a voltmeter, which we can see the output voltage, and an ammeter in series, that's this one here, so we can see how much current is going in and out of that output. And then it's connected to a whole 10 more inverter inputs, which is the maximum fan out that we came up with earlier, and that's what all of these little green LEDs are on. So the ammeter will tell us whether or not we are maintaining the correct operating conditions, and the voltmeter will make sure that the electrical characteristics are still correct. So let's start by looking at this on its own to see what the voltage and current looks like, just to make sure everything matches what we see on the datasheet. And then we'll put some LEDs on this output along with all of these inverter inputs, see how much more current it draws, and see whether or not the voltage goes out of the datasheet range. So right now the output of that inverter is low. So you can see we have just a bit over 10 milliamps going out of all of the inverter inputs and into the output of that one inverter. And that's still pretty well below the 16 milliamps that the datasheet asks us to stay under, so we're good there. And the output voltage is still within the datasheet range. The datasheet says it will never go above 0.4 volts as an output low voltage. And it's a bit close, but we're still in there. And then in the output high state, you can see we're really not drawing very much current at all, 0.08 milliamps, and the datasheet asks us to please not draw more than 0.4 milliamps, so we have quite a bit of wiggle room here. And the output voltage of just about 3.7 volts is a bit below the 5 volts that we would expect, but it's still pretty well above the minimum 2.4 volts that the datasheet says it will give us. So here we see with the maximum number of inputs connected to a single output, the current is still staying within the range that the datasheets ask for, and the output voltage is still staying within the range that the datasheet promises. And now we'll add a couple of LEDs here. One of them will be forward biased and turned on when the output is low, and the other one will be forward biased and turned on when the output is high. And right now I have some pretty large resistors here, 4.7 kilo ohms. So with those LEDs, everything still seems to be working, but let's take a look at those voltages and currents. So here in the output low state, we're still around 11 or so milliamps, so not that much more current is being drawn in the output low state. You can see the output low voltage is 0.42 volts now, and the datasheet promises that it will never go above 0.4 volts. So this is actually a little bit outside the range that the datasheet promises. But we can see on the datasheet that even though it promises to never go above 0.4 volts, even if it does, it should still be okay because the inputs to the gates are willing to accept 0.8 volts. So everything still works fine. And then in the output high state, we can see that we're drawing about 0.5, close to 0.5 milliamps, which is outside the range that the datasheet asks us to draw. It asks us to draw less than 0.4 milliamps. But the output voltage is still well above the 2.4 volts that it promises. So everything seems to be okay here, even though we're pushed a little bit outside of the datasheet boundaries. And now, let's swap out those 4.7 kilo ohm resistors with those LEDs for some much smaller resistors. I have some 180 ohm resistors. And so that will make these LEDs draw much more current, and then we'll see what happens then. Alright, so everything still seems to more or less be working. Let's take a look at the voltages and currents. Seeing the output low state, we're now drawing 24 milliamps, which is way outside the 16 milliamps that the datasheet asks for. And you can see the output low voltage has gone up above half a volt now, 0.54-ish volts, which is outside of what the datasheet promises of 0.4 volts. But again, since the inputs will accept up to 0.8 volts, we still have enough wiggle room and everything seems to work fine. And then in the output high state, we see that we're drawing about 3.5 milliamps, maybe a bit more, which is way above the 0.4 milliamps that the datasheet is asking us to draw in the output high state. So like, this is way out there. This is like almost 10 times as much as the datasheet is asking us to draw from the output. And the voltage has gone all the way down to 3 volts, but that's still above the 2.4 volts that the datasheet promises, so everything's still happy there. So I think the moral of the story here is that even if you have some pretty insane small resistor values, and you push these chips outside of the datasheet ranges, everything still more or less will probably work okay in most cases. Of course, this was specifically with the 7404, and there are also different flavors of these chips. There's the 74LS04 and the 74S04, and they all have different input and output circuitry, so they're going to behave a bit differently. And also just from one part to the next, they could vary differently, or from different manufacturers or different batches, so we're still not guaranteed to operate correctly. But for the most part, it's probably fine. So if you're going to be building your own circuits and testing them, you probably don't need to worry too much about buffering your LEDs. I'm still going to do it here just because I want to make sure everything is sort of the best it can be for all those weird edge cases that I can't predict, and because I already have the sockets soldered down onto the board, so I might as well.
So why even make this video if buffering the LEDs isn't actually important? Well, it's kind of fun to be wrong about things sometimes. That's how you know you're learning something new. And I honestly thought that these gates would just stop working when I put the LEDs on there. I actually had to rework my script and then re-record the test that I did. So it's a good reminder to always double-check your assumptions.
And you'll notice that I have another few sockets over here that are unpopulated so far, and that's going to be for my clock and clock multiplexing circuitry. Just like buffering the LEDs, it's probably not that important that I do it correctly, but I'm still going to do it anyway because I think it's interesting, and I'll talk about that in the next video. I'll see you then.